Hey everybody, in this video we're going to talk about the basics of energy and work. So first of all, what the heck is energy and what types are there? Before we get into all of that, I just want to make sure that you have in the back of your mind always when you're looking at problems in physics that always start with energy to try and understand what's going on, because energy is a scalar, the math is simpler. And if you can understand and solve the problem using energy, it's almost always the easiest way to solve the problem. So always begin with energy. And it's a physical thing, it's just a number that tells you the state of the system. It tells you how much you have. It's just an amount. So like this mouse has a certain amount of energy, this calculator has a certain amount of energy, I have a certain amount of energy. It's just a number. Think of it like kind of like money. It's the currency of the universe. It is just a number that tells you kind of what the net worth energy-wise is of the object, all right? It's a scalar without directions. Its units are joules. That makes the math simple. All types of energy have the same units of joules, whether it's nuclear, chemical, whatever. It doesn't matter. It's all the same. There are many types of energy, okay, but it's still all the same conceptual stuff. We just give it different names so we can understand it a little better. But as far as the universe is concerned, energy is energy. It doesn't matter if it's thermal energy or kinetic energy or nuclear energy. Now, we're going to talk about mechanical energies in this class just because we're studying mechanics. Our first type is kinetic energy. It's the energy of motion. There are two types of kinetic energy. There's translational, 1/2 mv squared, and there's rotational, 1/2 I omega squared. So they are the same equation, just in translational and rotational form. So Mr. Stick here has kinetic energy translational when he's displacing. He has rotational when he's rotating but not going anywhere. And then you can have both if you're moving from place to place and you're rotating. So look at this picture right here. What kind of kinetic energy does this system have? Well, the ball is moving, so translational. The pins are moving, so translational. The ball is rolling, so rotational. Some of the pins look like they're rotating, so they would have rotational kinetic energy as well. We'd have to add all that up to find out the total energy of the entire system. Our second type of energy is stored energy or potential energy, and it's always due to the interaction of two or more objects and the position those objects have relative to each other. So say, for instance, chemical potential energy. The arrangement of the atoms in the molecule relative to each other, their positions, determine how much chemical potential energy there is in the system. For planets, okay, we have two planets. The gravitational attraction between the two determines how much gravitational potential energy they have. One planet by itself cannot have potential energy. You must have two interacting objects that pull on each other. So here is our general equation for gravitational potential energy. It's negative big G m1 m2 over r, almost said r squared, over r. So you take the two objects and you find the radius between their masses. Remember, G, big G, is a constant that's on our constant sheet, universal gravitational constant. For instance, in this particular situation right here, we have the Earth, we have the Moon up here, and we have the Sun down here. Now, by the way, this is not to scale. The Moon is nowhere this close to the Earth. So if you want to find the gravitational potential energy between the Earth and the Sun, you would find the radius between the center of the Earth, or the center of mass location, to the center of mass location of the Sun. And that's how we would find our radius. We plug in our two masses. Now, what if we have the system of all three? Then this equation only handles two at a time. So we'd have to use the Sun and Earth and the radius between them, the Earth and the Moon and the radius between them, and then the Moon and the Sun and the radius between them, and then add them all up. Don't let the negative sign throw you. Turns out, because of the way the math works, that you have zero gravitational potential energy when they're very, very far apart. They're not interacting. And because gravity attracts, it ends up being a negative potential energy. Not a big deal. Okay, We have a simplified version of this equation when we're near the surface of a planet where the gravitational field is constant, where little g is a constant. So here, when we're near the surface of a planet, we can use mgy. The question is where's y 0? So in this particular case, we would probably use the valley floor for this rock. But you can pick it wherever you want. You can pick it up here if you'd like. You can pick it in the middle, wherever you want. So that's why this has a delta in it, because the delta difference between top to bottom won't change no matter where you pick your zero height for y. You can see that in this equation, or this picture right here. In this particular one, this is what most people do, is they pick y to be 0 at the bottom of the problem. That way they have only positive potential energies, and that's fine. But you could have negatives, it doesn't matter. The key thing is how you get from one place to another. Say we take this safe up into our apartment up top. We can take any of these paths, it doesn't matter. We're all going to have the same change in potential energy, whichever path we take. So it doesn't matter at all. Our second type of potential energy is elastic or spring potential energy. It's the energy of when you take something and you bend it or stretch it or compress it, and it wants to snap back to its original position. And that will be 1/2 kx squared, where k is a spring constant that we learned before in forces, and delta x is the distance it is from its original position, original shape, how much it's stretched or compressed or bent. So you can see that here, our delta x will not be this. This is the original length, 0.3 meters of the spring. So our delta x will be how far we stretch it from that spot when we pull it. So there's our mechanical energies. We have kinetic energy, which comes in two parts, translational and rotational. We have potential energy, which is gravitational, the general form for like planets, and then the form for when we're close to the Earth's surface, mg delta y. And then we have elastic potential, 1/2 kx squared. And that's it. There are other types of energy, but all these three are under the heading of mechanical energy, which is what we're studying. There's other types of energy like internal energy. This has to do with the movement and position of atoms inside of an object. We talk about that in thermal physics next year in AP Physics 2. And there are more, like chemical, nuclear, radiant, there are others, but we study those in different parts of physics. We got to have a heart-to-heart talk about systems. Choosing the system is all important because it determines how you're going to account for the energy. Remember, an object by itself can only have kinetic energy. So like this object right here, it can only have kinetic energy and internal energy because it has atoms. Okay, we study that in physics 2. So if we want to have other types of energies, we have to include the interacting object with it. So like for gravity, if we want gravitational potential energy, we have to include the object and the Earth. If you want spring potential energy, you have to include the object and the spring. If you want all three, then you got to include the object, the Earth, and the spring. Otherwise, the forces will be external, and that will make solving the problem different. Not wrong, just different. We're going to talk about the idea of work and how it changes the energy of a system. So, external forces that act along the displacement of the object will do work. Okay, and here is where this whole idea of systems come into play. How you're going to account for the force of gravity and the force of a spring. So here is a bunch of skydivers. This group on the left, the system is just the skydivers. I get to choose what I want the system to be. So if the system is just the skydivers, the Earth and gravity are external. So gravity is an external force. So that external force is pulling them down. They're moving down. So that force will be doing positive work on the skydivers, making them speed up. Now, on the other hand, if we define our system to be the skydivers and Earth together, then gravity is now an internal force in the system and will not be external, so it won't be doing any work. So how do we describe how the skydivers speed up in this case? Well, in this case, because we have included the Earth down below and the skydivers above together, then now they have gravitational potential energy. And as they fall, the gravitational potential energy turns into kinetic, which is why they go faster. So the idea of a system determines how you're going to account for this change in the system, whether you account for it in terms of energy or whether you account for it in terms of work. So work, the equation for work is that it's a force that's parallel to the displacement. If it's in the same direction as the displacement, then it'll be positive work. It's in the opposite direction of the displacement, it will be negative work. If it's at an angle, then we have to account for that angle and only use the part of the force parallel to the displacement. So here we have some examples down here. A stick figure picks up their child. Okay, they apply a force of 81 newtons up. The child moves up, so that's positive work on the child. Here we have a wagon that has a force on it at an angle. The wagon is displacing to the right. So this force is not parallel to this. Only part of it's parallel. So we have to use F cosine theta. That will tell us what the parallel component of the force is to calculate our work. Again, this is positive work. So positive work always adds energy into the system. So this child has gained gravitational potential energy. This wagon will be gaining kinetic energy due to this work. So look at our car over here on the right. In this case, the car is moving to the right at a constant speed. So I have a force of friction from the tires making it go forward. That would be producing positive work because it's in the direction of motion. We have drag force in the opposite direction of the way it's going. So that would be negative work. We have a normal force that's straight up and a gravity force that's straight down. Both of those are perpendicular to the way it's going. So they don't do any work by definition. Also, I have shown that all of these are the same size, like friction is equal to drag and normal force is equal to gravity. Now, normal and gravity cancel each other out, so they wouldn't do any work anyway, even if they weren't at 90 degrees, because they cancel each other out. But the friction force forward is doing positive work, the drag force backwards doing negative work, and since they're the same force, same magnitude, but in opposite directions, their work will cancel out. So the net work on this car will be 0 and it won't speed up. No gain in kinetic energy. And then we have the special case of an object that doesn't move. So there's a force on the wall, but the wall doesn't move. So since there's no displacement, then no matter how hard you push, there's no work done. All right, work is also the area under an FD graph. So let's go back to our stick figure picking up their child. So 81 newtons of force, and they lift the child 1.3 meters. And so if we graph that, this area underneath here also equals the exact same thing as if we just calculated it over here. So the area underneath an FD or an FX graph is our work. So for objects that don't have a constant force, like when you stretch a spring, the force gets bigger and bigger and bigger. Then you would plot the force as a function of displacement and find that area underneath. And this is actually how we find spring potential energy. There's the spring force equation. There's X. As we stretch it, the spring force gets bigger. And we find this area underneath here, it's 1/2 base times height, which turns out to be 1/2 kx squared, which is spring potential energy. Which brings us to our last equation. Work changes the energy of the system. So for a spring, the work that you do to pull it is equal to the spring potential energy. This father lifting up their child, the work that they put into the child gives the child gravitational potential energy. And in the case of a car, the force that pushes the car forward gives the car kinetic energy. All right, let's talk about power. Power is the rate at which work is happening, which also then means the rate at which the energy is changing for the system. So here we go. Power equals work divided by time. Power equals the change in energy divided by time. So here's an example. Jack and Jill run up a hill to fetch a pail of water, as seen in the figure. Jack and Jill are very competitive, so they make it a race. Here's Jack's mass, 80 kilograms. He runs up this 20-meter hill in 10 seconds. Jill, who has a mass of 60 kilograms, takes a shortcut and runs to the top in 7 seconds. Which one does the most work? Which one generated the most power? Okay, pause the video and see if you can figure out who does the most work, who does the most power. Pause the video. All right, our answer is, it's easiest in this one, I think, to just find the change in energy, because the Jack and Jill, they don't give us the velocity of them, so I'm just assuming they have a change in potential energy. And so they go from down here, 0 height, up to 20 meters. So they have a certain change in height, delta y, 20 meters. G is the same for both. And M, well, it's bigger for Jack than it is for Jill. So Jack does more work because he has more mass for the same G and Y. However, if we put the numbers in and divide by time, then we find out that Jill's power is greater than Jack's. So they both win. Jack does more work, Jill generates more power. Now let's talk about the big news of this unit, which is conservation of energy. Here's our equation for conservation of energy. This is the way I want you to work it out on the test. Is you take the energies you start with, and then you account for any work done, and then that's how much energy you end with. So when we try to solve an energy or work problem, the very first thing you have to do always is define the system. And this will tell us which forces do work and which forces provide energy. And then you need to decide if there's external work done by forces outside of your system. So remember, if the system is just the object, just Einstein, then any force on the outside, including gravity or springs, would be doing work. But if you include Einstein and a spring and the Earth, well, then those forces would be internal and they wouldn't be doing any work. Decide what kind of energies you have at the critical points of interest, and then set up conservation of energy. So here's our example. You got a roller coaster that starts at rest at point A at the top of a frictionless track of science. Okay, I want you to decide, what system do you want? Will there be any external work? And what types of energy are there at critical points? So, at the top is our first critical point. What's our system? Well, I'm going to choose the cart, the roller coaster car, and the Earth because I see it going up and down, up and down. So there's a change in height, so there's potential energy that could be involved here, right? So I'm going to choose cart, Earth. Now, is there any external work done? Well, what are the forces acting on this? Well, force gravity, but that's internal, so we don't have to worry about that one. And then there would be normal force as it goes around the track. But remember, the normal force is always perpendicular to the surface, and the car is always going to be going parallel to the surface. So the normal force is always perpendicular to the way the car is going. So therefore, the normal force in this case won't be doing any work. And it's a frictionless track of science, so no friction, so no work done by friction. So it looks like there is no external work done. So that means the energy we start with must equal the energy we end with at any point. So we're going to have potential energy here, and as we move through, as we go downward, we're going to pick up kinetic energy. I'm going to choose the lowest point down here as my zero height. Okay, now what's the question? Where will the car be moving the fastest? Well, whenever the kinetic energy turns all into potential. So it would be down here at the lowest point. And maybe here, it's hard to tell. The wheels have gone through the track in my drawing. The car is not going fast enough to make it through the top of the loop in point B. So remember, from circular motion, you have to be going a certain speed in order to make it through this loop. So let's say we're not going fast enough. What can we do to increase the velocity of the car right here? There's really three options. Well, really two options. Okay? We can either make sure that more of the existing energy is converted into kinetic. So we could lower the track down and make the loop lower. And that means that more of the potential we started with is now converted into kinetic. It makes it through the loop. Or we could start with extra energy here to increase the kinetic we have here. So we could start with a velocity here by, say, adding a spring. If we add the spring, we add more energy at the beginning. Or we could increase the height of point A, so adding more potential energy that can be converted into kinetic. Any one of those will work. All right, that's our basics for energy. So our next video, we're going to go through a whole mess of examples. So get ready to solve those next.